Now to prove that this L is regular, which follows from this, so we will construct a DFA for this L. So we will construct some DFA called fmin, and we will justify these choices, and we will show that this DFA accepts this language L. Now, how do we construct this DFA? So that construction is motivated by what we did before for this 1 to 2 part. Okay, so you remember this thing. So we showed that there is a bijection between this Q and equivalence class of Rm. So this CQ is the equivalence class of Rm. Okay, equivalence class of which string? Any string that belongs to CQ. So you can have multiple representations of this thing. So okay, for example, here we had this 2 thing, but they are same equivalence class, and we showed that the edges are like this. So from W on A you have a transition to equivalence class of WA, and here I have just removed this RM just to make the picture more readable, but here it actually means that it's equivalence class of RM. Okay, it's very important that in this picture we are talking about the equivalence relation Rm, and these are equivalence classes of Rm. Okay, so now in this theorem we are given this RL. Okay, so we are given L, and from there we can find RL. The RL is defined depending on L, and it's of finite index. So this is given. So here, in order to construct this M mean for this L, what we do is we look at the equivalence classes of this equivalence relation RL. Okay. So you remember the language for this was this thing. So the set of all strings which contain exactly 1 1. Okay, and if you look at the equivalence classes of RL, so it's not important how I compute this thing. So but there will be 3 equivalence class. Okay, and they are precisely these sets. Okay, and again you say that there are multiple representation of this thing, and you see that so this epsilon belongs to this set, right? So that is why this equivalence class is this. 0 also belongs to this, so it's this. 1 belongs to this, so this thing is this. 1 0 belongs to this, so this thing is this, and so on, right? So this is a partition of sigma star, right? So if you take union of all these things, so you get sigma star. Okay, so this ABC. So if you just take this, so this is a partition. So there is a partition of sigma star, right? And taking cues from here, we just construct a automata where the states are this equivalence classes. So the states are A, B, C. Okay, and the edge we put also following this. So we put epsilon to 1 1 to 1 1. And here again, just notice that again this to make this picture clutter free, we have removed this part in this picture, and here also. But here it means the equivalence class of RL. Okay, so here it is RM, and here it is RL. So it's equivalence class of RL. So just do not confuse between this one and this one. They are different. Okay. So yeah, so we construct the automata like this, and then we argue, we prove that this automata actually accepts this language L. So what we did here, how can we formally write that down? So as I said, the states are what? States are the equivalence classes of RL. Okay. So though it may look sort of an infinite thing because we are taking all the strings here and taking this, but you know that this is finite because this RL is of finite index. Okay, it's important. So that is why this Q is finite. Now you see, if I am making this thing, okay, so epsilon belongs to obviously the equivalence class of epsilon, right? And epsilon means you are at start state, right? So obviously the choice for start state is the equivalence class for epsilon, right? And then what will be a final state? So on 1 you reach this state, okay. So on 1 you reach precisely the state, this equivalence class of 1 in RL, right? And by the definition of this L, so in this particular example, so this thing is accepted by this L, so that means this 1 is in L. So in general what will happen, so so we take this all this X which are accepted by the language L, and we take the corresponding equivalence class to be a final set. Okay, again this is a finite thing, and it's a subset of this thing, right? Because it contains all the equivalence classes. It only contains some of the equivalence classes of X, such that this X belongs to L. And again the motivation is from here. So if you are processing something and if you say 1 0 0, so again this is equal to equivalence class of 1 0 0. So yeah, all those things, equivalence class of all those strings for which and the string belongs to the language. And then the transition function is what? It's from X to XA on symbol A. Now here we have to be slightly more, we should give an explanation, because see here the states are equivalence class of RL, right? So suppose you have some equivalence class X of RL, and we define this Y to be XA such that this X belongs to small x belongs to this capital X. So small x belongs to capital X means this X is actually equivalence class of this small x, right? So from X we are going to XA, and obviously there is a RL here. Now this should not depend on any particular choice of X, right? So this X, this capital X can also be equal to say some equivalence class of some X prime, okay? So the map is from this capital X to something. So if I choose small x and if I choose small x prime, it should not matter, it should not be different y here, right? So this y should still be same. So that means we require this property that if this equivalence class of x and x prime are equal, so then equivalence class of this xa and xa prime should also be equal, and that is true because of the this right invariance of RL. Okay, so that follows from the right invariance of RL, and to do this explicitly, so right invariance is here, right? So right invariance means if they are related, then I can put something here and still they are related. So this means that yeah. Sorry, here I have here I should take y. So for here I'm using y. So here I should take y. Okay. Yeah. So if this x and y denote the same equivalence class, then you see that xz and yz, they also represent the same equivalence class. So if I have x and x prime, so then x a and x prime a, so they also denote the same equivalence class. So this map that I am defining, it is well defined. That means it doesn't depend on any particular choice of x in this capital X. So no matter what small x we pick from x, we get the same capital Y. Okay? So that is why this definition is well defined. Okay, it doesn't really depend on any particular choice of x. So okay, once we have this, so this is the formal description of this thing that we explained via an example before, but this is the formal construction for any general case. Now, as I said, we will prove this thing, that language for this thing is L, right? And we will use induction on some string W to prove that if you and start from the start state is here, right? And if you process this, then you are at this state. So this is a state here, right? Because it's just all equivalence classes, and this should be the equivalence class of W. And this is quite clear, right? Because from epsilon with 1 we go here, with 0 we go here. So this is where this comes, and so it's pretty straightforward, but still we can write the proof here. So the base case is just you take this to be epsilon, and by definition of this delta hat, if you have epsilon here, then the result is just this one. Okay, and this one is this. So yeah, it holds that this and this. Now if you put this one, as I said, so first you process this x, you go to this state, and this is by induction hypothesis, because x is shorter than W, and then from here you process this A. So that means you have processed this whole of W, and from here by this thing, by our construction here, so we go to this, and this is, so this is just fine. So we prove this part, and this part shows that if I take the R of M min, so you remember the definition for this thing. So this dependent on the automata. So this is RL. Okay. So what was so the meaning of this RM min? So x is related to y via this RM min if they go to the same state starting from this Q0. Okay, sorry, this should be y here. Okay, and should have a y here. So just make note of this corrections. Okay, I'm going back and forth in slides, so this is also y. So just this minor corrections you should be careful about. Yeah, so yeah, just make all these corrections. Yeah, so this was the definition of Rm for any m. So here I have in particular this m mean, so they are related if they go to the same state. And then this says that this thing is nothing but the equivalence class of this, and this thing is nothing but the equivalence class of this. And in any equivalence class, not just some automata or anything, in any equivalence class, this equivalence class of x and y are equal if and only if this x and y are related via that equivalence relation, right? So they are related here if and only if they are related here, so that means they are actually equal. Okay. So it follows just from this part up to this part. Okay. And now once we have this and this, we can prove that the language is this one, because see, string belongs to our what was this again, some typo. So what I meant is L of m min. Okay, so in both cases it's L of m min, right? It belongs to I mean it is accepted by this m min if and only if it reaches some final state. I mean, after processing W, you reach final state starting from this one, right? So, and this tells you that this is nothing but this one. So this thing is this one. And what are the final states? Here, by our definition, we put all this equivalence class of x's such that this x belongs to L, right? So that means this gives you that this equivalence class for W is also a equivalence class for x for some x in L. Okay. So now these are equal, as I said. I mean, any equivalence relation, the equivalence classes are same if and only if they are related in that equivalence relation. Okay. And what was the definition for this? If you go back here, so they are related via RL if for all z, xz is in L if and only if yz is in L, right? So you here just take the special case of z equal to epsilon. So if you take z equal to epsilon, that means x is in L if and only if y is in L, right? So that means that x is in L if and only if y is in L, but L is this x is already in L, right? So this is how we defined this thing. So x is already in L, so that means W is in L, and you said there is a if and only if condition. Okay, so this is a if and only if condition. So that means this whole thing is a if and only if thing. So W belongs to this L min if and only if W belongs to L. So that means L of m min is equal to L. So there we have the proof that this L is actually regular. Now we have proved this thing involving these three statements. Now during this journey, what did we get? So you see, from here to here, it gives you a necessary and sufficient condition to decide whether L is regular or not. So it tells you that L is regular if and only if RL is of finite index. So this is also one tool to prove that some language is not regular. See, it's not only about regular languages. So you take some L, somehow you prove that the index of RL is not finite, and then you can conclude that that L is not regular. So this gives you another tool apart from pumping lemma. So far you only knew pumping lemma as a tool to prove that something is not regular. So this gives you another tool to prove that something is not regular, some language is not regular. And while proving this 2 to 3, so we showed that so here it really doesn't care about whether this L is accepted by some DFA or not, but if this is accepted by DFA M, so then we showed that the index of we showed that this RM is a refinement of RL. Okay, so this in fact came at the very first thing. So yeah, here even so in the first thing, so we showed that this is a refinement of this thing, and so the index of let it go. So then from here, yeah, even before proving this thing, we had that this RM is a refinement of RL if the L is regular. So yeah, so if this L is regular and it is accepted by this DFA M, so then RM is a refinement of RL. So the index of RM is at least as much of the index of RL. But now this number of this index of RM, so that is precisely the number of states in M, right? So yeah, here. So when we prove this part, this 1 to 2, okay, not 2 to 3, this 1 to 2 part. So we proved that this index of RM is actually the number of state, because each state corresponds to a equivalence class of this RM, right? So the number of equivalence class is precisely the number of states. So that means the number of states in this M can't be less than the index of RL. And then in this last part, here we have actually constructed automata for a regular L, where the number of state is actually the index of RL. You see that it's precisely the equivalence classes of RL. So this is fine. Not just this is finite. So this is saying that this is actually equal to the index of RL. Right. So that means whatever we constructed here, that contains the minimum number of states. So any automata M, if you construct, so any DFA M, if you construct which accepts L, the number of states in that M can't be less than the number of states what we have for this M min, right? So that means this M min, so this is a minimal DFA. You can't get DFA with fewer states. So this M min is a minimal DFA. Moreover, this minimal DFA is unique. Why? Because suppose you have some other M, okay, accepting L, and suppose you have the same number of states as that in M mean, right, which is index of Rl. So number of state is in this other, say, automata. So this is index of Rm, and if this is same as, if they have same number of states, then these two indices are same, right? But we proved that this Rm is a refinement of Rl. Okay. And if M is a refinement of Rl, Rl is a finite index, okay, and their index are same, so that can happen only if they are equal, right? So again, just go back to this picture. Yeah. So you have some R and R prime, their indices are finite. In fact, they are equal, and this is a refinement. So the partitions are like, you take the partitions here and you make further divisions. And if the indices are equal, that means that they are actually equal. So there is no further partition here. So that means R is equal to R prime. So here, yeah. So if you have some M with the same number of states as that of M mean, okay. So then this Rm is equal to Rm mean. So that means the automata is essentially same. Okay. You can give different name to your state. In one automata you can have state ABC, in another automata you can have state PQR. That doesn't change things. So it's just the changing of names. So it's just an isomorphism. So but it's essentially the same automata. So the minimal DFA is unique. So there is a very nice result. Now all of these things are fine. So these are kind of existential result, because you see I didn't tell you how to compute this equivalence class for some arbitrarily given language or whatever. So our very first slide was that suppose you are given some DFA. From here can you construct, say, the minimal DFA. Okay. So this is our next goal. So to give you actually a method, a recipe to construct the minimal DFA from a given DFA for that language. So it gives you an efficient algorithm to do that. So you can write a program so that if you input this thing, it will output this thing. Now you see that this Rm is a refinement of RL, right? So that means the equivalence class here is the union of equivalence classes here. These are the equivalence classes, and in this particular case, this A is union of this CA and CB, and this is this entire B. So this is the union of this CC, CE, whatever. So you see that given any DFA for any language, if you consider this given DFA M, and if you consider the minimal automata, so the minimal automata is unique, right? So you see that here some bunch of states will correspond to a particular state here. Correspond means so the equivalence class here is the union of equivalence class for this and this. So the equivalence class here is the the union of equivalence class for this and this and this. So in order to find this minimal automata, all we need to do is to identify this clusters, right? So we should partition this states and then combine this thing into one to get this thing. Okay. So now how do we find out whether, say, these two states correspond to the same state here, or these two states correspond to the same state here? Okay. So if I can find this thing for each pair, so for each pair of states, okay, in this given automata, because Q is here. So if I can find which pair of state correspond to the same state here, so then I can find this minimal automata. Now we will do this by actually finding out all the pairs which do not correspond to the same state. Okay, so then we remove all those pairs of different states, and then the remaining pairs are like this. Okay, so is that clear? So we find all pairs PQ in the state here, such that this CP and CQ, so they correspond to different state here, and they correspond to different state here means they they are not part of the same equivalence class here. Okay. So yeah, if I write that down mathematically, so we saw this. So the equivalence classes here are this, say this and this, and this means that this W1 belongs to this CP, and this W2 belongs to this CQ, right? So you take any two such thing, and you try to determine whether they belong to the same state in M mean. Okay. Now if this is true, then by the definition of this CQ, so P is this and Q is this, because what was this CQ, if you remember, so CQ was the set of all strings such that you reach this Q if you process this W starting from Q0. So yeah, this belongs to this, means this is actually P, this is actually Q, and as equivalence class I can represent this as equivalence class of W1 and equivalence class of W2, right? Now as I said, these are contained in equivalence classes of RL, right? So here the equivalence class of RL is A, B and this C, and say this CB is contained in A here, right? And we are trying to differentiate between CP and CQ so that they are not contained in the same equivalence class of RL. So now that means we are trying to find out whether this holds or not. Okay. So okay. Because you see this W1 is a anyway, so there is nothing to explain here. because if this CP belongs to this thing, then this yeah. Anyway, I mean, so if you have W1 for this Rm, which represents this CP, then this CP is actually a part of this W1 RL here, right? So we are trying to find out whether these two are, I mean, when these two are different. So these are equivalence classes of RL, and these two are different if and only if these are not related in RL, right? Okay. And when are these not related in RL? By the definition of RL, so what was the definition of RL? So this was the definition of RL, right? So they are related if for all z this xz belongs to L if and only if yz belongs to L. So they are not related if there exists z, so such that this happens but this does not happen, right? So yeah, so this is precisely the thing, that they are not related if there exists a z such that this belongs to L but this does not belong to L. Now this belongs to L if what? I'm starting from Q0 here. If you process W1, you get to some final state. This does not belong to this. That means you do not get to any final state. Okay. So that means there exists some Z such that yeah, this W1Z goes to some final state, but this W2Z does not goes to any final state. Okay. But what is this thing? So this is if you process this W1 first and then process Z. This is if you process W2 first and then process Z. And this is, we have it here, right? So this P is this thing and Q is this thing. So that means, yeah, this one. So that means the CP and CQ correspond to different states in this minimal automata M min, if and only if there exists a Z such that one of this, so say this belongs to F and this does not belong to F, right? So this is the condition we wanted in terms of PQ. See, this was our goal, and this is somewhat accomplished. I mean, it's not fully accomplished, but at least we have some definite condition. So how to differentiate between PQ if there exists a Z such that from P, if you process Z, you go to some final state, but from Q on that same string you do not go to a final state. Okay, once we have this condition, so this is what we just proved. Next goal is to actually verify this condition, right? Now we want to find all such pairs such that there exists Z and this is true. So this is just equivalent to this. But now we throw in another constraint, that the length of Z is at most I. Okay. So this thing will be a subset of all the pairs that we want to find here. Okay. And in the reason for doing this is to come up with a recursive definition for this DI. So starting from D0, we will construct D1, D2, D3, and so on, right? So this is just a subset with this added constraint. Now for I, what happens? For I, the length of this is 0, so that means this is only epsilon, right? So this is epsilon means this is P itself and this is Q itself, right? So that means this translates into this thing, that this D0 is all such PQ such that this P belongs to F but this Q does not belong to F, right? This is our D0. Okay. Now we want a recursive definition like this where we express Di in terms of Di minus 1, and that's quite easy to do because suppose your Z is of length I and you want to verify whether this is true or not, that this goes to F, this does not goes to F. So you take Z to be AX where this A is a symbol, right? So this A belongs to your sigma and this is a shorter string. So that means the length here is okay, so perhaps I should have used less than equal to, so that would be cleaner. So I should have used this, so this becomes this. Okay. Now suppose from P on A you go to this P prime, and from Q on A you go to this Q prime. That is dictated by this transition function delta for your given DFA. Okay. So then what is this in here? So this is like you first process, so you are processing Z, right? So you first process this symbol and then you process the rest of the string. So if you just first process this thing, the state you jump to is this P prime, because P prime is precisely that, right? From P you first process A and then you go to P prime and then you process this X. Okay. So this condition becomes that this thing is in F. So similarly this condition becomes that this is not in F, where this Q prime is this Q prime. Okay. So then you see that this P prime and Q prime belongs to this Di minus 1, right? Because it is being differentiated by this X, right? This X and X, where this X is at most of length I minus 1. So by this definition, this P prime Q prime belongs to this Di minus 1. So that means how can we find this Di? So Di should be all such pairs PQ such that there exists some symbol A such that if I do this, so if I take this thing and if I take this thing here, so these two things, so this P prime Q prime, so this should belong to Di minus 1, right? Now once you have this thing starting from D0, you can compute D1, from D1 you can compute D2, from D2 to. Now you see this thing means that if you hit say some Di such that it doesn't change in the next step, so that means from here to here it also doesn't change, from here to here it also doesn't change. So that means no matter what you do, I mean, it remains same. Now you see two states you can differentiate using this. So that means there exists some Z. So you take the shortest such Z, right? So there, if there exists some Z, so that Z must have some length, some n. So that means you can differentiate between this Q and P using a string of length some n, and you consider for all pairs PQ. So there should be a corresponding n for each pair PQ, and you take the maximum of that. So there exists some n, okay, for which if I put it here, so there exists some n such that this dn contains all the distinguishable pairs. Okay. distinguishable pairs, right? So there exists some n, and if you have at any point this thing, so you know that this is eventually is equal to dot 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 dn, right? So once you cannot discover any new distinguishable pair, you know that you are done. You do not need to do anything anymore. And now you have all the distinguishable pairs, so you remove those, so that means you are left with the pairs which should go together, so which should be like this, which should be put together, and then you have this minimal DFA. So just to demonstrate this thing for this so what was our D0? So it is all such pairs such that one is in final state, one is not a final state. So that means on one hand you have this ABF, and another you have this CDE. So all pairs where one component is coming from here and another component is coming from here. So AC, AD, AE. So you see AC, AD, AE, and then BC, BD, BE. So BC, BD, BE, and then FC, FD, FE. So FC, FD, FE. So all these things are distinguished. Okay, you know that they are not going to go into the same state in your minimal DFA. So then what? Then you compute this thing. So you already have this D0, and then from here you try out all the symbols. Okay, so here the only symbols are 0 and 1. So here you try out both 0 and 1. Take some then you compute this thing and see whether this thing belongs to this di minus 1 or not. So let's say this A and F. Okay, so you take A and F. By the way, this A I am here using as a symbol, so this has nothing to do with this state being named as A. Okay, so this A is just name of the state, and this A is just some 0 or 1, so just some overlapping of notations, but just do not confuse between this thing and this A. They are different. So here I am talking about this state A, okay, and say the state F. Okay, so now we see that if I take, say 1, okay, this is what? This is C, right? And if I take delta F1, so this is what? So this is F itself, right? So now if you look at CF, right? So this CF was already here. It is already in D0, right? So that means we have discovered that this AF should also be distinguished in D1. So this AF distinguished. So similarly we can distinguish B and F. And once we get here, so if we compute D2, we will see that there is no more pairs. So that means we have discovered everything. So that means what? This tells you that AB is not distinguished. That means AB should go together. And this tells you that C and D are not distinguished. This tells you that C and E are not distinguished. That means C, D, E together are not distinguished. And this is kind of redundant. So So yeah, this block tells you that C, D, E are not distinguishable, so they should go together. So C, D, E goes together, and then F remains as a separate state. So now if you do that, yeah, so you get this thing, okay. And once you get this thing, the transitions can also be derived from here, because you see, you treat this as some kind of island. You see that from this island on 0 you end up in this island, okay. So this 0 is kind of showing that if you are here and if you process a 0, you get back to this set. And if you are here, okay, if you process a 0, so on a 0 you get back here, on a 0 you get back here. So on a 0 you remain in this set, so on a 0 you remain in this set. But on a 1 you move to this part. Here again, from here on a 1 you move here, from here on a 1 you move here. So that means on 1 you move to this part. Similarly, from here on a 1 you move to this island, on a 1 you move to this island. So these are like islands, and these are like bridges. So the transitions can also be written down from here. So if we take a slightly more complicated example, so here it has given the example of the algorithm, but the point is the syntax is kind of like old programming language called Pascal, but you can read this as a pseudo code. This is quite understandable, and but this is same as, so we already discussed this thing, so you do not even need to go through that. So this gives you the algorithm. You start with this thing and you repeatedly compute this Ti, and when you are done with this condition, you stop and you take remaining pairs and you club those together. So here again you see that this is the only final state. So from C to any other state you should make the difference. So AC so AC, okay, BC, DC, EC, FC, HC. So these are gone in D0, right? And then say you are distinguishing say this say B and D. How can you distinguish? Because from D on A you go to G, from B on A you on 1, sorry, from D on 1 you go to G, on B on 1 you go to C, okay. And now you see that this CG was already distinguished, right? So it was already distinguished in D0, and now you are saying that from B on 1 you go to this, and from D on 1 you go to this. So this B and D should be distinguished. So in D1 you have this BD. So here, so this in D1 you can put this mark here. So similarly in D1 you will discover some other state. In D3 you will discover some other state. So it's you should actually stop the video and try to figure out this D0, D1, D2, and you will see that finally these are left, okay. So this means what? This means what? AE, okay. So that means this A and E. So this you should put together, okay. And then this B and H. So B and H you should put together. Okay, so this you should put together, and this is done, this is done. And then you have F and D, so this and this. So I don't know how to write. So F and D, so that should go together. Okay, so now if you do this, so maybe we shall call this thing, say, capital A. We shall call this thing capital B. So this thing I call capital B. Let's keep this C, and this we can call, say, capital D, and then let's call this capital E. Rename this thing. So what we have here is something like this. So we have A, and then we have a B, and then we have a C, we have a D, and then we have a E. Okay, so what are the edges? You see that from this thing on 1 you go to this D. Okay, so these are together as a D. So from A you put H to D on, say, 1. Okay, and on 0 you go to B. So on 0 you go to B. So from B on 0 you go to G, which I call here as E. So from here you can go to E, you call this 0, and from 1 you can go to C. So by 1 you go to C, and then from D on 0 you go to C. So this you have, and on 1 you go to this E from this D. So from D to E on 1, and from E on 0 you get back to this thing, and on 1 you go back to this A. So here on 0 you have this loop, on 0 you have this loop here over E, and on 1 you get back to this thing capital A. So from here to this capital A on 1. So this is the minimal DFA looks like after you have computed this thing.